But quantitatively, this is a hard problem. But qualitatively, we could do a lot. All right, and so we'll tackle some of the qualitative ways that we can talk about bonding in chemistry, how we represent the wave functions of a molecule, some of the strategies we use. But when we want to get the quantitative data, we'll see very quickly today that we don't have a lot of options, especially on the board. We're going to get to a point where there's nothing we can do on the board. We have to approximate it numerically, and so we'll let a computer do that. So I kind of want to talk about the theory, kind of background of how we're going to build molecules with atoms, put atoms together to make molecules today. Maybe we'll do a toy molecule, talk a little bit about how we combine atoms together, just qualitatively, introduce a few ideas mathematically about it, and then on Wednesday we'll do some examples and look at some actual numbers. We'll do some calculations. Actually calculate some orbitals. All right, so what I want to do today is I want to take, let's just start from the beginning. We've talked about the hydrogen atom so far. Right, our one exactly solvable chemical problem, right? One electron. Right, we have exact wave functions. Which have numbers n and l and m sub l. Right, and of course we have the 1s and the 2s and the 2p's and the 3s and the 3p's and the 3d's and so on and so forth. Right, we have all these orbitals, different energies. Right, and so the question is what happens now if we take two hydrogens, exact energies, and we also have exact energies. So I'll just add that. Right, we know the wave functions, so we know the energies. Right, so we have a kind of a baseline thing we can start with, right? We have a building block. Hydrogen atom is going to be our building block, right? And so the question then is how do we put two hydrogens together to make molecular H2, right? And then we're going to ask the question, well, what if we want to do something other than H, right? What if we want to go to helium, right? What if we want to go to argon? We want to go to carbon. We're going to have to think about, well, how can we treat carbon like a hydrogen atom? Talked a little bit about this. The idea is that we're going to represent, right, we have this baseline kind of building block, the hydrogen atom, its wave functions, and we're going to represent the bigger atoms as combinations of hydrogen wave functions, and then we're going to treat the molecules as combinations of multiple atoms as well. So there's two layers of addition here. So I'll just kind of generally talk about the idea. So for multi-electron atoms, heavy atoms, we're going to represent, so let's say for the helium atom, we're going to represent of course there's two electrons in helium. I kind of talked about this briefly a couple weeks ago. The idea is that we're going to represent the wave function of one of the helium electrons, let's say the first electron, as a sum of wave functions from hydrogen. So maybe there's a little bit of 1s in it, maybe a little bit of 2s, maybe a little bit of 2pz. Right? We can add as many as we like, right? By completeness. Right? The completeness postulate if these wave functions, if these wave functions right here, the sub-wave functions, if you will, the ones that we're adding, if those satisfy the Schrodinger equation, so if the C1s, Psi1s, and so on and so forth, this addition satisfies H psi equals E psi, then so does the big one as well. So if I apply H to this sum, that also is going to give me energies with the Schrodinger equation. Okay, so if the Schrödinger equation works for one, then it works for, if it works for each one, it works for a sum of them as well. That's what completeness is. You can always take if you have one little function that satisfies the Schrödinger equation, then a sum of those little functions also satisfies it as well. It's kind of messy, I apologize. But the idea is that, yeah, so this is, of course, a real wave function, has a real energy. This is 2, this is 2, and so the sum also is as well. Right, so we're going to add them together. And again, this is just an approximation, but it's the only approximation we can make. All right. And in fact, what math will show you that the real wave function for helium is equal to the limit as the number of functions goes to infinity of that sum. Let me call it n to n of Ci psi I. These are the hydrogen wave functions. So if I take that limit, if I sum up infinitely many hydrogen wave functions to represent the helium, the wave function for one of the helium electrons, I get the exact answer. So the approximation approaches the correct answer as our guess gets bigger. Right, and in fact, this is that problem 3. This is that problem 3 on the midterm, the variation theorem. It says we don't know the real wave function. The idea was you didn't know the real wave function, so you make a guess. Here we only have one in the problem 3. There's only one wave function. You just guessed it, right? Which is a one wave function, not a sum of them. But we saw that it gave you an answer. The energy is somewhere within 10 to 15% of the real answer. And if I were to add multiple more guesses to that function, the energy would get better and better. And so if you were to do problem 3, but instead of having one guess function, you have an infinite sum of guess functions, then you'd get the correct answer, perfect answer. Okay, so that's really powerful. The idea is that the kind of key idea is the bigger the guess function, the more accurate the approximation is. So we can always when we want to approximate something, when we want to come up with a wave function to represent, basically we want to build something out of hydrogen wave functions, because those are the only things we know. Right? The only real ones the only things that we know the functions for are the hydrogen atom. So if we want to represent a helium electron, we can make a choice. We can make a very, very simple guess. Right? Maybe it's one function or two functions. Maybe it's the 1s plus the 2s or something like that. Really simple, really small approximation. But if we feel like we need more accuracy in our calculation, we can add more terms. Right? We can just keep adding things to our guess function. Right? We can make this sum bigger and bigger and bigger and bigger. And that should theoretically allow us to make more and more accurate predictions for our bigger system, in this case helium. And this is exactly the way that quantum chemistry works. When you do a quantum chemistry, you put your molecule together, you want to calculate its structure or its energy or its properties. We can't solve the Schrödinger equation for that molecule, but we can make an approximation of its wave function by basically approximating it as a sum of guess functions that represent the individual atoms. Right? And each of those atoms might be also approximated by a sum of hydrogen atoms. Right, so the way this is going to work, we'll come back to this idea in a second. The idea is called the linear combination of atomic orbitals theory, LCAO. And let me explain a little bit about how this works. Let's assume you have a molecule with n atoms, right? Each atom electron is represented by a guess that is a sum of hydrogen-like atomic orbitals. So if you have, let's say if you have n atoms and m electrons, okay? All right, so the wave function for the mth electron in the nth atom is going to be equal to some number of terms. It doesn't matter how many. Let's just do it from I equals 1 to, I don't know, k. Doesn't matter, just some number. And you're going to have a coefficient on the outside times a wave function, a hydrogen wave function. So that might be the 1s, that might be the 2s, 2p, our choice. Right? We can choose as many as we want. It doesn't matter. The more we put, the more accurate the answer is going to be. But we don't need to use all of them. And I'll explain a little bit why that is once we kind of break this down a little bit more. There's some reasonable choices we can make for how do we build our atoms, our big atoms out of hydrogen atoms, if you will. There's a reasonable choice to make for a good approximation. And then what we're going to do is we're going to represent the molecular wave function. So the function for the whole molecule as a sum of the atomic orbitals, which are these YMNs. Okay, so the molecular wave function, which I'll write psi like this, psi molecule, is going to be a sum from I equals 1 to some number, k, what doesn't matter, well, actually, it's all the way of all these electrons, so it's n times m, or something like that. It's probably not even that. It's over m electrons, I guess, of some coefficient I times the wave functions of each of the atoms. Okay, so let me just write that down. Each atom is a sum of hydrogens, and each molecule is a sum of atoms. Now, this seems complicated, but the reason why we do this is because if we think about the wave function of the molecule, it's represented as the sum of the wave functions of all the atoms, each of which are made up of wave functions that we know. Right? So we know the actual formula for psi I. We make a choice. They're hydrogenic, right? They look like hydrogen wave functions. And so that means that we know the exact functional form of our approximation for the wave function because we're taking a sum over atomic orbitals, which are made up of hydrogenic orbitals that have a fixed amount of known amount of hydrogen. Right? We know the hydrogen wave function. So everything's based off of hydrogen, but we're doing two sums, right? We sum over each atom is summed over each electron, has an approximation for each of the electrons. And then our molecule wave function is the sum of all the electrons of each atom. So there's two layers of sums here. Okay, so again, this is very, very conceptual. All right, and we'll actually work out an example, lots of examples these next couple weeks that use this idea, where we're going to represent atoms in a simple way with hydrogens. Right, we're going to think of as a helium atom or a carbon atom as a bunch of hydrogens added together, and then we're going to represent our molecule as a sum of all those atoms. We'll see how this works out. It's pretty straightforward. Okay, so let's start with a simple example. Let's do the simplest we can think of, which is H2. All right, we know what hydrogen looks like. All right, we know all of its wave functions. So all we need to do is put two hydrogens together. Baby's first molecule. H2. Okay, So let's just set up H2 in the way that we set up the hydrogen atom. Let's draw some coordinates for the electrons and the nuclei, and come up with a Hamiltonian, some energy formula for it. All right, make some accounting for all the different energies that's in H2, different electron interactions, electron nucleus interactions, all sorts of things going on in H2. Make a sum of it, and then let's kind of analyze this equation a little bit. So the coordinate system I want to use, it's pretty straightforward. I'm going to have my two nuclei, two hydrogens. I'm going to call one HA, so this is the nucleus, the proton of hydrogen A in my molecule. I'm going to connect it to HB, which is the nuclei of atom B, hydrogen B. I'm going to say that the distance between them is big R. Right, that's the distance. And then there, again, H2 has 2 electrons. So we have 2 electrons floating around somewhere. So let's put one here, E2. Let's put another one here, E1. All right, and we have some distances to take. All right, remember, we're dealing with electrostatic attraction, so we need to measure the distance between the nuclei and the electrons. And of course, that goes across both combinations. We need to measure the distance between A and 1, so we'll call that R1A. I think that's the, yep, that's what I use. This is R2B, right, the distance between nuclei B and electron 2. There's going to be a cross distance, R1B, and R2B, or R2A, right, the cross distances. And of course, there's going to be the distance between the 2 electrons. So we'll call that R12. Okay, those are all of our distances, right? So what do we have here? We have the distance between the nuclei, the distance between each nuclei of each electron, and the inner electron distance, R12. Okay, so the energies that are accounted for here. First is the kinetic energy. I'm not going to write down the terms for this. I'm just going to write down some qualitative terms for these energies. We don't have to write down the Hamiltonian. Kinetic energies, we write E's, of electron 1 and electron 2. We also have the kinetic energies, right? The nuclei can move as well. So we have the kinetic energies of the nuclei. A and B. And then we have a bunch of electrostatic terms. We have some repulsions, some attractions. Right? So remember that the protons are positively charged, so they repel each other. So we have the repulsion between nuclei A and B. All right? And then we have, of course, the repulsion between the electrons. And then we have attractions between the electrons and the nuclei, of which there are 4. So let me just write this down real quick. So this is repulsion between nuclei A and B. This coordinate is R. This one is R12. And then there's 5, 6, 7, and 8. These are the nuclei electron attractions. So that's R1A, R1B, R2A, R2B. Okay, so in the Hamiltonian, the big energy operator, there's going to be a term for each one of these. A kinetic energy, some repulsion terms. There are 6 repulsion terms and 4 kinetic energy terms, one for each nuclei and one for each electron. So there are 2 terms. Let's write it down, 2 terms. This one has 1 term because there's 1 repulsion, 1 term for electron, and 4 for attraction. All right, so we have this really, really, really long Hamiltonian, right? But we can write it down, right? The terms of these terms look no different than the hydrogen ones. Just as a hint, like this is going to be equal to the kinetic energy operator T. Kind of looks like h bar squared over 2 me times dx d squared Right, you've seen this operator before. It's the second derivative one, right? No different than the hydrogen atom, but you just have, now you have 2 for the electrons, and you also have 2 for the nuclei. So here the nuclei energies are proportional to minus h bar squared over 2 times the mass of the proton instead of the mass of the electron. And all of these terms look like minus e squared over 4 pi epsilon naught times whatever r it is. Right? They all have the same form. Right? So what this, if you think about it a little bit, this looks like a bunch. If we just had one electron around nucleus, we would just have the hydrogen atom. Right? Same terms for the hydrogen atom. This kinetic energy, we have this potential energy. That looks like minus e squared over 4 pi epsilon naught 1 over r. Right? This is the attraction, electrostatic attraction. Right? But we have many of them because there are many nuclei and many nuclei and many electrons. Right? So we can do this for any molecule we want. Right? We can have 100 electrons and 50 nuclei. It's kind of a weird combination, but bear with me. We can have as many as we want, and we can write down every single term. Right? We can look at every electron with respect to each other, every nuclei with respect to every electron. Right? We can write down the Hamiltonian for this, no problem. The problem is you can't solve it. The problem here is that the only molecular or atomic Schrodinger equation that's exactly solvable on the board is for 1 electron. Right? The moment you have more than 1 electron in your system, you can't solve it anymore. Right? We can't do the same thing where we write our Schrodinger equation and then solve it for the wave functions and the energies. You can't do that anymore. Right? So this is why we have to make approximations. Right? So the moment you go to H2, it has 2 electrons. Schrodinger equation is not solvable anymore. I mean, you can write it down. You know that the wave functions exist because you can measure them. Right? You know that H2 is a real molecule. But you can't actually represent them analytically. You can't have I can't just write down a function that says this is the exact wave function of H2. So how do we get around that? Well, what we're going to do is we're going to represent each electron as a hydrogen electron. I got 2 hydrogen atoms, that should make sense. And we're going to add them together. And then we're going to represent our molecule as a sum of those 2 hydrogens, right? We're going to take a complex problem and represent it as a sum of easy problems. Right, so in general, because quantum mechanics is linear, we can always tackle problems like this, where we want to represent a complex problem. We can always represent it as a sum of simpler ones. And if these aren't simple enough, we can represent them as simpler ones. Right? We can even represent simple as simpler ones. Right? We can just keep going down the list and start adding things until we get to a point where we can approximate everything exactly. And we're usually guaranteed that as long as our guess is long enough, as long as we add enough simpler functions, if you will, as long as this is long enough and this is long enough, we'll get an accurate answer. And our accuracy depends on how many terms we add. But in general, we know if we go towards infinity, if we get our guess gets better and better and better, our answer's going to get better and better. Okay, so what we're going to do then is say, okay, well, we can't do anything about this. Right? We can represent our system exactly. Right? This is an exact picture of the hydrogen molecule. 2 electrons, 2 nuclei. But we just can't solve it this way. Right? So we have to make a guess. So what I want to talk about today is kind of that guess. Right? I'm just going to talk a little bit about the kind of structure of such a guess, kind of the ideas that we can do and what we get out of it. I want to, again, talk about before we really jump into math, how we actually do this problem. I want to make one more approximation. So here's an interesting thing. is that we have two classes of particles that are moving. We have nuclei and we have electrons. Okay? And if you think about it, if we change the position of the two nuclei, right, maybe we move them closer or further apart, imagine they're vibrating against each other, right? R is changing. Well, then that's going to affect all of the other terms, right? If the nuclei come together closer, you're going to have more repulsion energy here. That's going to want to push the nuclei out. And that's going to affect the motion of the electrons. So in this simple picture of H2, the motion of the electrons depends on the position or the motion of the nuclei. Okay, they're all correlated to each other. The way we would represent that as a wave function is that the wave function of H2 is going to be a function of, well, R, R1A, R2B, R2A, R2B, R2A. Did I get that as all? No, I missed one. Sorry. This is R1B, excuse me. And R12. We have this function that's just of all these different coordinates. This is really ugly. Right, the last thing we want to do is represent a wave function in all of these variables where they all depend on each other. Right? So we have to make a simplification. And there's a really, really interesting one that we can make that's critical. Right? If we were in a situation where we had to worry about if the electrons are in a certain position, it'll affect how the nuclei interact with each other. Right? Everything's touching each other, everything's feeling each other, they're all kind of cross-contaminated, if you will. They're all feeling each other out collectively, so they're all dependent on each other. And that's not fun, because now we have a function where we have to track the position of the electrons, the position of the nuclei, the relative position of the two electrons, the relative position of the electrons to the nuclei, and it's really ugly. That's just a messy function to do. So what we're going to assume now is here's something interesting, is that the observation I want to make is that the mass of the proton divided by the mass of the electron is around 1800. Right, so the electron is about 2,000 times smaller than the proton. And so if we look at the kinetic energy is proportional to 1 over the mass, 2 me or 2 over mp. That means that the relative kinetic energies of the electrons versus the protons, so the kinetic energy of the proton versus the kinetic energy of the electron, is also around 2,000. All right, so that means that on average, the electrons are moving at the same energy if they have everything all being equal. Electrons move 2,000 times faster than the protons. So that means, therefore, that when electrons move, all right, so if we measure the time scale at which electrons move from one position to another, and they tend to move on a time scale of about a femtosecond or so, attoseconds. So these tend to be, the time scale tends to be on the order of anywhere between 10 to the minus 18 to 10 to the minus 15 seconds. All right, so think about, like, for instance, this electron oscillating from one atom to another like this. That time scale tends to be on the order of about 100 attoseconds or so. Very fast. So when they move on this time scale, they move instantaneously relative to the nuclei. So their motion, right, the vibrational motion of these atoms, right, the oscillation of the nuclei when they move is on the order of the vibration, and that time scale is 1,000 to 10,000 times smaller. So that's 10 to the minus 15 to 10 to the minus 12 seconds. Okay, so when the electrons move, the electrons are bouncing around, moving around really fast, and relative to that time scale of an electron motion, the nuclei haven't even moved. Right? They've barely even jiggled. Right? So electrons can bounce back and forth between two limits of a wave of its orbital, right, from one end to the other of this molecule 1,000 times before the nuclei ever complete one vibration. Right? So what we're going to assume then is that the kinetic energy, that the motion of the electrons is independent of the nuclei. Okay? So what we're going to do is we're just going to say, well, the nuclei relative to the electrons, the nuclei don't move at all, so let's just freeze them. Right? Let's just fix their position, and therefore their energy doesn't change when the electrons move. Right? They're always fixed. There's no change in their position. So there's one nuclear energy, if you will. There's one orientation of the nuclei that the electrons see. And the electrons just move around that orientation. Right? So let me write here. I'll leave out my terms because we'll need them for a second. Let me change color. So this approximation that the electrons move much faster than the nuclei is a key one for, in fact, we'll see this term come up time and time again this month. It's called the Born-Oppenheimer approximation. Right? After Max Born and Julius Oppenheimer, as in the head manager of the Manhattan Project, Oppenheimer. All right, and what they say is that, again, is that the nuclei, we'll call this the clamped, or the nuclear motion in a molecule is uncoupled, which means it doesn't affect it to the nuclear motion or the electronic motion. And what this means is that the molecule of the wave function which is a function of the position of the atoms of the nuclei and the electrons. That's one big function. It's a function of, this is the nuclei and the electrons. I'm just going to write it as a simple term. Because the position of the nuclei has nothing to do with the electrons, or rather the position of the electrons has nothing to do with the nuclei, they don't talk to each other, this function splits into two terms. One that's a nuclear term and one that's an electronic term. So this is so we have the nuclear wave function, which is a function of just the positions of the nuclei, times an electronic wave function. That's a position of the electrons. Right? There's two functions, one for the nucleus and one for the electrons. Right? They don't talk to each other. They're completely separate. Right? This is the key approximation we do for everything in quantum mechanics. The reason why the way we can calculate these structures, or chemical properties, even doing spectroscopy. The fact that we have, I'll say this in a second, the fact that vibration, rotation, electronic, all of these different types of spectroscopies are separate. Right? We don't talk about them as being one thing. They're different techniques that give you different information. Is a product of this. Or if we didn't have this, if the electronic motion was dependent on the nuclear motion, then there wouldn't be all these different spectroscopies. There would just be one spectroscopy, and all the motions are coupled together in a very complicated way. Right? And what this leads to is that the energy of the molecule ends up being a sum of separate terms. So there's the nuclear energy, there's the electronic energy. All right, so this is a repulsion between two nuclei. This is attraction. Two nuclei plus repulsion, inter-electron repulsion. And then there are the terms that are, and then there is also the term proportional to, oops, that's not E. That's also not an E. That's an E. Vibration, energy of the rotation of the molecule, energy of the translation of the molecule, and energy of whatever else, other stuff. All right, that's like the nuclear spins and stuff like that. So we'll call this like spin. Stuff that NMR, nuclear spin, or electronic spin. Right, those are the things that NMR looks at. But what this does is that all of the basically the repulsion energy is very large, but the nuclei don't move that much, so it's fixed. You have an electronic term that's large and complicated. Right? That's the electronic part. That's the motion of the electrons in the molecule. And then we have these smaller energy things that we've already talked about. Right? This is just basically a diatomic vibration for H2. This is a rigid rotor part. This is the particle in the box. And this is NMR, basically, stuff. Spin orbit coupling, things like that. Things that we talked about, spin. Right, so we've already talked about most of these terms, right? We've talked about the rigid rotor, right? Treating H2 as a spinning molecule, looked at its vibrations, right? The vibrations of it. We've talked about putting H2 in a box, right? We've only talked about an electron in a box, but you can put H2 in a box too and get translation. And so we're left with these two terms. This nuclear one that's large, it's fixed because the nuclei aren't moving. They're fixed to a specific position, so this is just a number. And then we have this electronic term that's a little more complicated because it's dependent on the coordinates of all the different electrons. All right, so this is kind of, this term right here, in fact, is the key term to understand bonding. Right? Bonding is just the sharing of electrons across atoms, right? The interaction of two electrons or multiple electrons in a system. And that's this term right here, right? This is the bonding term. Right? This is bonding. All right, so the Born-Oppenheimer approximation is an amazing assumption. And it turns out to be good to up to 1 part in 10 to the 5. It depends on the molecule, but it's a very accurate approximation. And if we assume that the nuclei don't move with respect to the electrons, instead of having all of these motions all together in one really complicated thing, we can split them out. And we have a term devoted just to the bonding part of the electrons, right? The interaction between electrons and their nuclei. And then motions of the nuclei together, collective motions of the nuclei, right? All the rotation is taking a molecule, a nuclei, and spinning them. Vibrations making them translate with respect to each other, and translation just moving the whole molecule in space. And we can also say that this is effectively 0 as well. Just you don't have to worry about it. It's really small. It doesn't take a lot of energy to move a molecule. But that's really powerful because we've already talked, right? We don't have to worry about the rotation and the vibration of our molecule anymore because they've just separated out into smaller terms that we can deal with separately. Right? We've already done that. So secretly, we've been actually working our way up to completing the total energy of the molecule or the wave function of the molecule because we've done the vibration, the rotation, the translation. We've talked about spin a little bit, and we're just left here with the electronic term, right? Bonding. Right? That's all we have left to do. We've already evaluated everything else. Right? Now we have to think about this nuclear term, but that's okay, right? It's not hard to do this with one more step. The idea is the way we're going to measure, so how to measure, ultimately what we're going to do is how do we measure the electronic energy? Right? And the way we're going to do that is what's called through the clamped nuclei method or approximation. Which means that we're going to fix the atomic nuclei to a fixed value of R. All right? So we're going to fix this term. We're going to calculate E nuclear at R. All right, we've got two, in hydrogen, we have two, molecular hydrogen, we have two protons sitting at some fixed distance with each other. We can just calculate how much attraction is between them. It's pretty easy, right? It's just E squared over 4 pi epsilon naught times the distance between them, or H2. I'll just write that. E nuclear is proportional, is around E squared over 4 pi epsilon naught R, right? Just calculate it. It's just a number. And then calculate, and then solve the Schrodinger equation for the electronic wave function using our LCAO approximation, linear combination of atomic orbitals that I talked about earlier. Okay, so I'll just write that as a sum of smaller wave functions. Okay, just a sum of smaller wave, simpler wave functions that give us a bigger one. All right, we solved the Schrodinger equation for that. So what does that give us? Well, so what we're going to do is I'm going to make a plot now of R, the internuclear distance. This is the bond length of H2. All right? And then I'm going to calculate the energy of the system as a function of R. Total energy of the system as a function of R. So what I'm going to do is I'm going to take I'm going to start with my atoms close together, and I'm just going to move them further and further apart, right? I'm going to step R, right? Remember that the energy of nuclear repulsion is proportional to 1 over R. So I'll just draw it. The nuclear repulsion looks like this. This is the nuclear repulsion. So if it were just up to nuclear repulsion, this molecule would want to just disassociate completely, right? Because the electrons, the nuclei repel each other, and they want to be far apart. So there's obviously an electronic part that we include in this. All right, so I'm going to take each one of these points, some R value, and then I'm going to fix R to that value and solve the electronic part, right? I'm going to do the two electrons together, and I'm going to calculate the electronic energy as a function of their positions. Now let's think about this qualitatively. Maybe we can come up with a formula or a structure, a plot of the total energy of the system, electronic plus nuclear, by just looking at what we think this system looks like. So let's do this. So here's my hydrogen, here's my other hydrogen. Remember, this has a hydrogen. We're going to start with two hydrogens together. We're going to have one spin up and one spin down, and we're going to put them, they're just hydrogens by themselves. So these are psi 1s, I'll call this A and B. Like that. So I have two atoms, two hydrogen atoms. The distance between them is R. And each atom, when they're at their respective limits, is just a regular hydrogen atom. So each atom is in its 1s state. All right, so you have one electron in a 1s orbital, just normal old hydrogens. All right, and so what does this look like in terms of wave function? So if I draw the psi squared for these, so what I'm going to do is I'm going to draw a straight line. This is the position of B. And this is the position of A. And of course, the distance between them is R. And what do the wave functions psi 1s look like from here? So this is psi 1sa squared. So that's where the electron is in the hydrogen A, roughly. And then I'll draw it for the other molecule. There's an r squared here as well, but that's just because we're in spherical coordinates, we need to add an r squared to it. And then for B, we have the same thing but facing the other way. Like that. This is psi 1sb squared. Okay, and so now what's going to happen as R comes together, as R starts to close in, what's going to happen? Well, that means that as R starts to close, then this wave function is going to start moving towards the center of my plot, and this one's going to start moving together. Electrons, we're just treating each atom by themselves, separately. Okay, and we're going to bring them together. All right, so eventually they might be at some intermediate step. So this is, I'll call this long distance. All right, and there's like going to be some intermediate distance. I'll just kind of roughly draw them. Same idea. And the wave functions are going to start to approach each other. Like that. And another one over here. Like that. Okay. And then there's a close one as well where they're like on top of each other. So I'll just draw that really quick, but you can imagine what that looks like. Something like that. Whatever. This is close distance. I'm bringing the atoms closer and closer together. Okay, so let's think a little bit about what does this tell us. Okay, so what we're going to do now is we're going to represent H2, the wave function of H2, as a superposition or a combination of the orbital for 1sa, right, this one, the electron on 1s, and then one for 2s. Or sorry, 1sb, right, for the second electron as well. Right, so that means then that the square of the wave function for the hydrogen atom is going to look like C1 squared psi 1sa squared plus C2 squared psi 1sb squared plus C1 C2 of psi 1s psi 1s, the overlap between the two, if you will. Okay, so there's a part that looks a lot like the psi squared, looks a lot like the wave function of the electron, just the lone electron on A. Looks a lot like the lone electron on B. And now there's a cross term that's proportional to the product of these two wave functions. All right, so if we apply H psi equals E psi to this, big psi, we're going to have C1 H applied to psi 1s A plus C or squared plus C2 H applied to psi 1sb squared, these are squared, plus C1 C2 H bar psi 1sa psi 1sb. Okay. So when we evaluate this out, we're going to get C1 squared. And so what I'm going to do this is I'm going to now multiply both sides by psi, like that. And this is just the average value of the energy, which equals to E times the integral of psi squared times whatever integral we have. All right, so let me work this math out really quickly. So the Schrodinger equation there's our Schrodinger equation. If we represent big psi as a sum of two little psi's, then what we can do is multiply both sides by psi. And then I'm going to integrate. Like that. All right, so I'm going to add an integral times psi to it. Right, so we can do this. Right, this is just the expectation value. The expectation value is equal to the energy times the overlap of the wave functions. Okay, so what that means is the bonding, the energy of the system is dependent on how much the two wave functions of the two atoms overlap each other, right? If you look here, there's very little overlap, right? There's a little bit where they overlap right there, right? So the integral of psi A, psi B is close to 0 here. But as they start to come together, right, if you think about it, there's a little bit of area under both curves that they share. Right, so psi of psi A, psi B is greater than 0 here. And then when they're completely overlapped, then they both share basically the same area under the curve. They overlap almost completely. Right, so here psi A, psi B is close to 1. I'll come back to this plot in a second. So what that means is that kind of qualitatively, we'll look at this in more detail, qualitatively, bonding interaction requires an overlap, a spatial overlap, right? They have to overlap in space of atomic wave functions. And I think if you remember the description of covalent bonding from general chemistry, this idea that atoms share electron density across bonds, that's what this means. Right? There's some probability that the electrons, basically what this means is that there's some probability that electron B, so if they overlap like this, what does this mean? This means that there's some probability that electron B is in the area of atom A, and there's some probability that electron A is in the area of atom B. Right, they overlap, they share each other's density, right? And here there's no overlap, right? So there's very little probability that electron A is in B space and vice versa, but when they overlap, there's some probability that electron B, so electron 2, how do I write it? Electron B in A space and electron A in B space. Right? So when the overlap is not 0, then that means that there's some probability that the density of the electrons, the probability, is shared between the two atoms, and that's a bond. Right? So overlap is a bonding interaction. Of course, the problem is, if you think about it, well, that must mean that the more bonding there is, the better. The more overlap there is, the better. Right? So why isn't it like this? Right here, they're overlapped completely. They share each other's density almost perfectly. But the problem we haven't considered here is that this ignores electron, and nuclear repulsion. So in order for this close distance to be happening, that means the nuclei have to be close together and the electrons have to be close together. And of course, that's repulsive. So even though the electrons actually prefer this orientation, they want to be on top of each other completely, there's a repulsion energy that pushes them away. So there's a balance. So I'll go back to that plot again. I shouldn't have erased it. I apologize. of R versus the energy of the molecule as a function of R. Right? So this is the nuclear repulsion. Right? So likewise, so again, what I'm trying to say is that there's a favorable energy associated with bonding, electrons overlapping each other, but you don't want them to overlap so much that you're up here where everything repels each other, right? So here you have good wave function overlap, but high energy, high repulsion. And here you have poor wave function overlap, so poor bonding, but no repulsion. Okay, so that must mean that the correct answer is somewhere in between, right? We have to find the Goldilocks limit. We'll talk a little bit more about how the formula for this works. Yeah, we don't really quite have the time today to do it. So on Wednesday, we'll talk about how is the energy of the electrons affected by the overlap. We'll actually work out an equation for it. But the idea is that they can't be so close that the nuclei repel, and they can't be so far away that they don't talk to each other anymore. So once you do the analysis and you solve for the electrons, you do this analysis, you calculate the energy of the system as a function of the overlap based on a fixed distance. And what you find is a curve that looks like this. So at close distance, actually, sorry, I have this wrong. Sorry, it goes negative. I apologize. Like that. Close distance, large energy, right? And this is far distance, low energy, right? But there's this region here, and we'll see this, where you have, so this region here is at negative energy relative to 0, which means that the wave function overlap, the bonding overlap, stabilizes the system. Remember, so again, the limits of our energy at at 0 distance is the nuclei on top of each other at infinite energy, and the other distance is the nuclei at infinite distance at 0 energy. So the molecule, as a function of its position, the energy of the molecule will be at those two limits. And so there's going to be a region, though, where the overlap is favorable, and that lowers the energy. Right? And so the presence of this minimum implies a bond. This energy minimum here, notice that the energy as a function of the position is 0. This is a minimum, which is a bond. Right? So on Wednesday, we'll calculate this. All right. On Wednesday, what we'll do is we'll pluck in. What we'll do is we'll simplify the problem a little bit. What we'll do is we'll pluck an electron out of here. We'll ionize H2 to make H2+, and that's an exactly solvable problem. There's only one electron. Right, so what we'll do instead of looking at H2 is we'll look at H2+. We'll be able to calculate all the integrals and stuff, talk a little bit about how it works, and what we'll find is that there's a certain range of distances between nuclei where the electrons have favorable overlap. They're not so close together that they push each other apart, and they're not so far apart that they don't talk to each other at all. So there's this Goldilocks region where the electrons talk to each other and do so in a sort of like not a compassionate way, but a cooperative way, and that will lower the energy, and that's what creates a bond. Right? This overlap, favorable overlap. Right? There are going to be situations where we can combine two atoms together and we'll never be able to find a favorable overlap. For instance, if I were to replace this with both spin up, if they were both spin up like this, the electrons will repel each other. Because remember that because of Pauli exclusion, 2 electrons of the same spin can't be in the same place. They're fermions. So if I had 2 atoms like this that came together, there's not going to be ever any favorable overlap. In fact, the integral has to be 0, and they're going to repel each other. Right? So for this combination, there is no bond. But when I combine it like this, Pauli exclusion doesn't apply. There is no repulsion between 2 fermions because they're in 2 different states. They can come together and overlap favorably. Right? So we'll look at combinations like that. Right? We'll think about how do the number of electrons and how the electrons arrange themselves into energy levels and orbitals, how does it affect bonding? Right? Not surprisingly, when we get to helium or neon or argon, right, those have complete valence shells, right? They have all their electrons are paired. So obviously they don't really form, we'll see that they don't really form bonds because there's no reason to pair electrons together because they're already paired in the atomic forms. Right? But in H2, they're both unpaired. You have 1 electron per atom. They're both unpaired. They're going to come together, right? Because you know electrons want to pair. And the reason why electrons want to pair is exactly for this reason, right? There's this when you have 2 electrons of opposite spin, you bring them into a region together close by, not too close, but close enough. There's a favorable overlap. There's some probability that electron 1 is in electrons 2 space and 2 in 1s. That exchange, that's a favorable interaction. The energy for that is negative. It's an attraction. Right? And that's a really, really powerful thing, right? Is that we often think of electrons repelling each other. Right? You think by charge, electrons repel each other. But by spin, electrons of opposite spin are always attractive in some Goldilocks region. So that's one of the amazing things about electronic matter is that when you think about charges, you think, okay, you have 2 electrons, they're negative, they don't want to be anywhere near each other. But that neglects, and that would be true, but electrons also have spin. And the fact that they have spin allows 2 electrons, again, both have negative charges. The fact that when you have opposite spins allows them to be in the same place together. Right? They can combine together, and they can interact with each other. And and they do so with this favorable overlap, wave function overlap like this, and that causes attraction. Right? And so, in fact, you can show, I don't know if we'll have time to do this in this class, but you can show that all electrons bound in matter, or all electronic matter, if you will, right? All atoms, all materials, attracts itself, attracts each other. There's a really beautiful, maybe, I don't know if I told this story. I don't know if I've told this in this class yet. There's an experiment that you can do. You take 2 plates of metal. Have I talked about this today? The Casimir effect. Have I talked about it in this class? Okay. So it's a really interesting effect. And it was predicted in the 50s or 60s. It wasn't proved until the 90s. It's a very hard thing to see. You take 2 plates, 2 metal plates, all right, just aluminum, just flat plane of aluminum, 2 plates of aluminum. Right? They're electrically neutral, right? You don't apply any voltage to them. They're just plates that are floating in air, not in air, in the vacuum. Nothing interesting going on. Right? And you put them on a stage so that they can come close to each other like this. Right? So you just have 2 plates that are just floating next to each other. Nothing interesting happening. Right? You've accounted for gravity. They're just floating in the vacuum. Right? You've set up an experiment so that they effectively float in the vacuum. Okay? There's no gravity. They're just floating. Right? And you change the distance between them. What you find is that when you take those 2 metal plates, and if they're flat, they have to be really, really, really flat. Really flat, electrically neutral. Because having them not flat will cause more effects than you would imagine. But if you bring them close together, what you find is that at a certain distance, Of course, if they're right on top of each other, you can't push them together, right? They repel each other, right? When you put two plates together at zero distance, they can't come together. There's some resistance there, right? Because that's the electrons repelling each other, right? And at long distance, they do nothing. At long distance, when you have them apart, they're just plates. They just stand there. Just aluminum plates. It's really boring, nothing going on. But if you bring them close enough together at the right distance, and that distance turns out to be somewhere on the order of a nanometer or so, really, really small distance, just a little larger than the interatomic distance between each atom and the plate, bring them to 1 to 10 nanometers, they attract each other. There's a net force. So you take two plates of about a meter squared surface area, and you bring them to about a nanometer and 10 nanometers in distance, they attract each other with about a 10 millionth of a Newton. It's a tiny, tiny energy. Right, tiny energy. But the reason why is because the electrons in the plates, you have some that are spin up, some that are spin down, and when they overlap, when the wave functions of those two electrons in each of the plates start to overlap, right, when you get into this region where you're close, where they're close but not touching, the electrons will exchange. Right, you'll take an electron from plate B and it'll go to plate A. A plate A electron will go to plate B. They exchange. As the electrons in B move, that makes the ones in A move, right? So if the B ones move up like this, the A ones will move down like this to get away from it, because they still repel. And these motions, these correlated motions, of electrons exchanging across the identical electrons exchanging across the plates, or the correlation of motions of electrons in each of the plates, those are attractive energies. It causes an attractive energy. You can show that anything that's got electrons in it, bound in it, metals, gas phase atoms, molecules, right? Even helium, has an attraction. Right? And the reason why is because when you put two electrons close together of opposite spin, you get favorable wave function overlap between them. Right? And that lowers the energy. Right? And that stabilizes systems, and it causes an attraction. So even though electrons repel each other, if you put them in a bound state, right? You put them around the nucleus, you can make them attract each other, assuming their spins are opposite. All right, it's called the Casimir effect. There's a chemistry version of it called the van der Waals effect, or the London dispersion force. Maybe if you guys remember from a million years ago, there's the different types of intermolecular forces. There's hydrogen bonds, there's ionic bonds, dipole-dipole interactions, and then there's the idea called these van der Waals forces, or dispersion forces, London dispersion forces. And these are the Casimir effect for molecules. You take two atoms, say two helium atoms, or two molecules, two H2 molecules together, literally any molecule, bring it together with another one, they attract each other. They will always form some small amount of wave function overlap of each other, assuming that they aren't both the same spin, right? The electrons they can combine in a reasonable way. You will always form a stabilizing bond between two molecules or two atoms. Now that bond might be meaningless, right? We'll look at that, right? When you bring two helium atoms together, it does stabilize it, right? You form a helium bond, but that bond is incredibly weak, and so the moment you sneeze at it, it falls apart. So we'll talk about a little bit about the relative strengths of these bonds, and why some bonds are stronger than others. But everything comes down to this, the wave function overlap. How well can the overlap of one atom, the electrons of one atom, overlap with the electrons of the other one? And can they do it in such a way that doesn't cause the nuclei to repel each other, or the electrons to repel each other? Right? So we'll look at that more carefully. We'll be able to work out an equation for this, and we'll be able to come up with a formula to calculate the energy, or at least have a qualitative idea of what the energy states of hydrogen looks like. Right? We won't be able to calculate numbers because we can't solve the equation, but at the very least we can figure out what happens to these wave functions when they combine. When the atoms combine, what's the net product, if you will? What's the net wave function, the molecular wave function? And what we'll find is that, again, there are sums and differences of the atomic wave functions. And I'll show you some of the math associated with that, right? So we'll do some qualitative analysis of these orbital combinations to get some ideas of what the energy levels of hydrogen look like. And then we'll go to the computer and have the computer calculate it for us, and we'll show that our qualitative picture is exactly the same as the quantitative picture. Right? That even though we can't do the calculation, we can still set the calculation up correctly. Right? We can set it up on the board we have a sense of what's going to happen, but we can't calculate the exact number, right? We can't exactly calculate the exact energies, but we know what's going to happen, and then when the computer does it, it agrees with our prediction. Right, so we'll do that on Wednesday. Okay, that's all I have for you today. We'll return the molecules on Wednesday. Problem set will be posted in hopefully 15 minutes. Yes?
What is this for?
Oh, E nuclear. So it's the energy of the nuclear repulsion. Yeah, you're welcome.
I see it now. I couldn't see it before.
Sorry. Yeah, you too. Sorry about that.
Oh, no, it's fine.
In middle school, I got or not middle school. Kindergarten, I got a lot of frowny faces for my E's. So you can see I haven't learned much since then. No, I had to go to a speech therapist though because I couldn't. My L's and my W's were mixed up. I kind of sounded like a.
I had to go to the counselor because I wouldn't talk to anybody, and they thought that like there was something going on at home, but I was just like really quiet.
It's just antisocial.
Yeah.
I had to go to somebody because I had that other.
I got it. Yeah. So I used to say instead of sleep, I said sweep. And
I feel like every kid does that.